So I want to review and kind of bring everything together. And when we're talking about bringing everything together, we're talking about a couple of key points about the repeated measures and the independent measures, or the within or between. And again, remember these terms are interchangeable. ANOVA. So the first thing to remember is that the ANOVA itself is an omnibus test. It tells us a difference exists somewhere, but doesn't say where the groups are different. And the reason for this is about probability, that when we're doing statistical tests, specifically inferential statistical tests, we want the obtained test statistic that we compare to the critical value. But the reason we're doing that is we're wanting also a marker of probability. And if we're running multiple tests on the same data, that marker of probability doesn't know we're running multiple tests. Therefore, we need to run an omnibus test that basically is adjusting for the fact that we're doing one large test. Is there differences somewhere? And are those differences, wherever they are, large enough that we can be confident that probability marker of P05? In other words, we are basically accepting there's a 5% chance we're wrong, but there's a 95% chance that this difference, wherever it is, occurred due to an implementation or a difference in our IV and not due to random chance. It simply just says that something's going on. If that is significant, we then need to do additional testing, and that's why we use the term omnibus test. It tells us it's the first test, it's the overall test, but it releases us to now look at additional tests where we're not as worried about probability. We don't need to look at the probability other than is it a significant difference. Which groups are different from each other, and that's usually done with post hoc tests. Post hoc tests basically act as a series of paired t-tests. In other words, they're comparing each group to each other group, and you can think about it again. If we have three categories, category 1, 2, and 3, if we were going to test them with t-tests, we'd need to run a t-test on 1 and 2, 1 and 3, 2 and 3. However, instead, we're going to create a single post hoc test that's simply going to tell us what is the honest, significant difference that we're looking at. Each group is compared to determine which is different. We are looking at the Tukey's test. However, there are in fact, there's quite a few other ways to test this, but for most ANOVAs, the Tukey is the most appropriate test, and it's an easy way to look for those differences. We could also do a priori t-test, and this means a priori is referring to the fact that we could be looking at, I run an ANOVA, I have multiple categories, but the only thing I'm interested in is there a difference between group 2 and 3? So if by theory we're only really caring about one particular difference, we could use a t-test in that case. In other words, that now becomes parsimony, simplicity, the simplest test to run, because it's not looking for multiple differences, it's just looking for a difference based on our a priori or before the fact hypothesis of our data set. This is going to be fairly rare, but again, everything that we cover in statistics, there's almost always a little caveat. It is what we do most of the time. However, there's always different situations. As I said, there's additional post hoc tests other than Tukey's honestly significant difference test, or HSD test. However, they're for very specific situations with very specific types of data. By the way, if you ever wondered what Tukey looks like, there he is. This is the guy that actually created the Tukey honestly significant difference test. And again, I just like looking up little bits of history about the people that have actually designed these terms that now bear their names. So just as a reminder, if we are running multiple t-tests, there is a way that we can actually get that significance back to making sense. In other words, if for any reason we're in a situation where we want to run multiple t-tests in the same data set, and for some reason it's not appropriate for us to run an ANOVA, we can do what's called a Bonferroni adjustment. So remember that one of the things we get with any inferential test is our error rate, our p-value. And the type 1 error in this case, we set it at p is less than 0.05, basically meaning there's a 5% or smaller chance of claiming an effect when it was just due to chance. This is for, again, running one test and assuming we're only running one test. The probability is based on the idea of one test. If we are running multiple tests within the same data for some reason without an omnibus test first, we need to make a Bonferroni adjustment. And there are other statistical adjustments that we can do to get our p-values back in line, but this is the most simple and the most common. We simply take our alpha and we divide it by the number of tests. So for example, if we have an alpha of 0.05, but we're running 3 tests, our new bar for accepting a significant t-test is 0.017. So it's harder now for us to be able to claim a difference, but this is adjusting for the fact that we're running multiple tests. It basically says that if we accept a significance of 0.017, that means that when we're claiming significance, knowing that we ran 3 tests, we're much more likely to be under across those 3 tests, that 0.05 barrier. In other words, it's kind of a stand-in for not having an omnibus test initially. If we want to estimate the type 1 error rate with multiple tests, basically our equation is 1 minus alpha raised to the number of groups. So again, we can run through this. So alpha is our p-value, c is the number of tests. So for example, if we are looking at 3 tests and we put this equation in, we actually find out that across those 3 tests without a Bonferroni adjustment, the chance that any one of them is wrong is 0.14. There's now a 14% chance that even if we said all 3 were significant at 0.05, the chance that any one of them is actually an error is actually up to 0.14. So again, these are ways to kind of ask, if we have to run multiple t-tests, what do we need to do to make sure that that p-value is still reflective of an overall or omnibus test of the data? So let's just review independent measures ANOVAs, and then we'll review dependent measures ANOVA. So again, the independent measures ANOVA, often referred to also as the within measures ANOVA, is looking at a single independent variable with 3 or more levels on a continuous dependent variable. And the big difference here again is the degrees of freedom and the fact that the bottom of the equation is using mean squares within. In other words, total variance, including the variance that differs from group to group to group, dividing the actual MS between, which is a measure of the actual effect size. Again, the degrees of freedom in this case, the between is the number of groups minus 1, and the degrees of freedom within is the number of total participants minus the number of groups. So in this case, 2 and 12 tells us, well, going backwards, 2 minus 1, or 2 plus 1 would be 3. So we know that we originally had 3 groups, so 3 minus 1 is 2. And 12, so 12 minus k, we know we had 3 groups, so 15 minus 3 would be 12, so 12 tells us there was 15 participants. So not only does this tell us our markers for how we evaluated the significance, the degrees of freedom, 2 and 12 is what we use to find our critical value, but also it lets us know by kind of doing backwards math how many groups there were and how many participants. In this case, our F is 4.07. That's our obtained test statistic. And again, looking at the chart, we find that it's below 0.05. And if we were doing this in SPSS, we would be getting, again, we would ignore the corrected model and intercept the first 2 rows, and we'd be looking at the 3rd row, which will actually be typically named the actual independent variable name, in this case, study type. That's going to have, again, our degrees of freedom, our mean squares, and right below it is going to be our within measures, our error. Taking these 2, we're going to be able to actually calculate our F, then it'll look at significance, and SPSS will provide us our partial eta squared, which is a measure of effect size. So again, when we take a look at this, how we report this is F2, 27, and again, we're getting those degrees of freedom directly from SPSS. And again, 2, that tells us that there were 3 groups. 27 tells us there was 30 participants. We have the actual F, 14.93. We have the fact that it is, its p-value is 0.001. Again, we never report a p of 0.000. There's always a chance we're wrong. And finally, because it's significant, we report the effect size, partial eta squared, 0.53. Please note that the F, the p, and the partial eta squared are all in italics. Whenever we're using references in statistical analysis to actually report those analyses, we're always going to italicize the various initials and symbols. So again, this is what we're getting when we look at the between subjects test, and we're getting this data as well. Now, while we're on this table, again, I want you to kind of think mathematically. We can also go backwards. So again, F is being calculated by the mean squares, the column right before it. If we actually take 1042.5, which is the mean squares of study type, and divide it by the error, 69.815, that's where we get 14.932. And the mean squares is basically the sum of squares divided by the degrees of freedom. So again, if we go back all the way to type 3 sum of squares, that second column after the name of the variables, we're going to see under study type 2085. If we multiply or divide that by the degrees of freedom 2, that's where we get the mean squares. Likewise, error is 1885. We divide that by 27, that's where we get the 69.815. If we're looking at repeated measures, 3 things are changing. The top of the equation is not really changing. The bottom is. Our MS is no longer within. It is simply error because, again, repeated measures or basically when we're looking at the repeated measures, we're actually looking at a between design where people are measuring the same thing. In other words, the same people in each group, or they've been matched up. And in that case, we don't have to include individual differences in our error term. We can use MS error, basically just the error, which is why it's more powerful. The bottom of the equation is smaller, so when we divide an MS between, we're dividing it by a smaller number, and we get a larger F. Also, the degrees of freedom change. So between is the number of groups minus 1, so that's pretty much the same. But the bottom is different. It's the number of groups minus 1 times the number of people in an individual category minus 1. So again, we're getting a slightly different equation at that point. And if we get SPSS, we're going to get a lot of differences in how it reports it, but the information is pretty much still there, and it works the same way. We're still finding study type. We're just looking at sporicity assumed, and we're also then looking at the bottom error. And again, these work the same as we saw before. If we look at the mean squares, we divide that by our degrees of freedom. That's where we get, if we take the sum of squares, the second column, we divide that by the degrees of freedom, which is the third column. That gives us our fourth column, mean squares. And this happens for both the study type and the error type. If we look at that fourth column, mean squares, if we take the mean squares of the study type divided by the mean squares of the error, that gives us our F. And then based on the degrees of freedom and that obtained test statistic of F, we can take a look at a chart or let SPSS tell us what is significant. In this case, again, the significance is 0.000, so it's less than 0.001, which is what we report. And again, we got our effect size partial eta squared, which we would report because there is significance here. Reminder, this doesn't tell us where the difference is. It just says that there is a difference. And again, we'd report that F, we'd report the 2 degrees of freedom, we'd report the obtained test statistic, whether or not it's significant, and if significant, we report the partial eta squared. So again, repeated measures versus independent measures theoretically. Independent measures ANOVA has generally some of the assumptions. We have an access to a larger sample size. We may be not able to test and retest the same people over and over, and we're worried about maturation or carryover effects. And again, maturation effects are that people are getting better naturally over time. Carryover effects are that because people are in multiple conditions, they're becoming more and more aware of either your outcome measure or the study in general. Theoretically, when we're looking at the F, what we have at the top of the equation is basically all of the error, including the differences between the groups, divided by just the differences between the groups, and in both cases we have experimental error as well. When we're looking at repeated measures ANOVA, generally we're going to use this technique when the number of available subjects is limited. So for example, if I only had 10 people, if I broke them up into 3 different groups, that would be 3, 3, and 4. Those are very small samples. But if I used a repeated measures ANOVA, I have 10 people in every condition. So you can kind of see how this can be a very useful tool when we have a smaller number of people. If we're actually trying to make overtime comparisons, if I'm actually looking at how people improve over time, in other words, maturation isn't a concern, it's what I'm actually interested in, this is a much better method to use. It does reduce error by removing individual differences, and therefore it's easier to detect an effect. Carryover effects can still be problematic, and that's still a concern that we have to be thinking about, is are people, because the measures are no longer independent of each other, it's the same people in each condition, they're also going to start to learn what the experiment is about, and they're also going to get more experience with your outcome. But theoretically, the F in this case is simply the difference between the groups and experimental error divided by experimental error. We've removed individual differences in our equation. And again, I've shown this chart again before. This is the exact same data set, but using the two different methods. Repeated measures ANOVA versus independent measures ANOVA, and what actually happens. And you can kind of see how the effect of removing that individual difference data actually changes the equation. So the top equation is a between subjects design. We get an F of 9.38. The exact same data put in as a repeated measures design. In other words, we've told the statistics, don't calculate individual differences. Assume they're the same people. The total numbers across the board are generally smaller. However, that F actually ends up being larger. And again, this is an indication of how these two are different and how repeated measures are more powerful. So briefly speaking, we are now at a point where we've added a fair amount of statistical techniques to our decision tree. Again, we can ask how many variables. If there's more than two, we can ask, is it continuous or categorical? But that, again, is something that we're leaving off for a future time. So at the moment, we're looking at how many variables, one or two. There's only a single variable. We just have an outcome. We're basically looking at a t-test or z-test for independent samples. We're comparing that one outcome to previously known data. If we have two, the categorical IV has how many levels? In other words, our IV, we're assuming it's categorical and our DV is dependent. If it has two, we're at a between or within subjects design question. If it's more than two, we're at that same question. It's simply asking, are we doing a t-test or are we doing an ANOVA? If both variables are continuous, we're using correlation or regression. So if there's only two levels of our categorical IV, if they're between subjects, we use the t-test for independent measures. If they're within subjects, the t-test for dependent measures. Likewise, if they are three or more categories in our IV, again, if it's between subjects, we use the independent measures ANOVA. If it's within subjects, we use the repeated measures ANOVA. And finally, if we actually have multiple variables, 2 plus, in other words, we have an outcome, continuous DV, and we have multiple categorical IVs, we're talking about the factorial ANOVA, which is what we're going to be covering next.